right. So if we can get into today's class here. All right, so yesterday I introduced through the video trig identities, and just to re-walk you through this in case you didn't get a chance to watch the video yet here. Okay, so for Unit 4, we're dealing with trig identities, and earlier in this course here, we talked a lot about some of the basic trig identities, right? Those Pythagorean identities, and our favorite one is cosine squared plus sine squared equals 1, or sine squared plus cosine squared equals 1, right? That was our favorite one. And so when we looked at Lesson 4.1, we talked about all of those different identities that we have for our trig functions, and we did this thing called proofs. And luckily for those who were in Algebra 2 today, we got a brief discussion on proofs. But again, the whole point with proofs is that you are proving that something is true, right? You are proving something is true. You're making both sides of the equation equal to each other through either definitions, through simplification, right, through all of these different processes, and that's what we talk about here in this 4.1. All right, and proofs are going to become really, really important for you when you get to calculus, right? When you get to calculus, you're going to be asked to prove a lot of different things here, okay? And a proof is a good discussion on how do you know what you know, right? Well, this is the equation I have. Well, why? How do you know it, right? And walking yourself through that. And I wish we had more time to talk about it, but it would be really awesome. And you can relate proofs to things beyond just mathematics, right? So you can relate proofs to things beyond just explicitly math equations here, right? Like we have equations for, if we relate it back to your chemistry class, right? You guys, we dealt a lot with radioactivity, right? And looking at radioactive isotopes and how fast they decay, right? And that thing called half-life, right? So using that relationship that we know for half-life, we could prove that carbon-14 dating method, right? We could prove that carbon-14 dating method, right? And hopefully you realize here that that's how we develop new equations, is using what we already know and manipulating it through equivalent expressions or through new discoveries here. All right, so that's what we talked about in 4.1. In 4.2, we expounded upon those trig identities to including not just the Pythagorean theorem or our basic trig functions and changing those guys. All right, I will let you know 4.2 is very, very meaty. All right, it is very hefty. It's a very dense little lesson here. So I would really make sure you set aside some time to go through this actually on Apex. Yes, watch the lecture, but I need you to make sure you really go through this because it's 12 pages here, but it's got a lot of new equations real quickly. All right, so making sure you go through that guy. All right, and so now we're going to finish up today with 4.3 here, and this is the application of identities. So we're going to look at the application of identities. We have one quiz here today, and then when you finish that or over the weekend, right, you're going to be responsible for doing the Unit 4 test here, okay? It's got a nice overview of all the identities. It's got a nice review of calculator skills, some extra credit practice, extra credit discussion, and then obviously you have your CST here, and that's the only thing you have to do, right? So I don't assign weekend homework in PreCalc, right? I'm not assigning weekend homework in PreCalc. So again, technically what I'm saying is today you should finish 4.3 and 4.4, but again, since you have a weekend, feel free to take it, right? You should just be done with Unit 4 coming into Monday here, all right? But if we look at applications of these identities here, all right, so we should now have the ability to kind of recognize some of the more familiar trig identities, all right? And you have that review sheet and your study sheet that have all of these different trig identities. So those are the equations that are under your tool belt, right? Those are there for you to use and manipulate in order to make these equations a lot easier here. All right, so again, that goes to that whole taking your inventory thing. When we're looking through problems, right, we take our inventory. Well, again, that's why you take inventory, so you can see what you have and see what you can use. All right. So, for example, here, if we look at these two expressions here, all right, algebraically, this is a large task here because we have a cosine x and we have a sine x here. All right. But most people would solve this using a trig identity, right? They would combine it and try to make a trig identity here. All right. And we have some clues here in other things, right? Essential in calculus and physics to see how we could solve this even further. All right, so if we look at this first thing, obviously we're gonna use it later on. So we have this human cannonball. So let's look at what this is and how this application would work here.
For some reason, you have decided on a career as a human cannonball. To ensure your safety, you plan on doing a little math analysis.
Naturally.
The horizontal distance you will travel depends on the angle of elevation of the cannon, given by theta. It also depends on the initial velocity, since the faster you are shot, the further you will go.
Okay, so of course we're obviously joining the circus here, and we're going into our cannonball career here. All right, so we've got to take into consideration, of course, how fast are we going, how high are we going, what's the angle of which we're being shot out at, because obviously the ultimate goal there is safety. The ultimate goal is safety.
Remember the gravitational constant that arose in your studies of simple harmonic motion? If you assume that there is no air resistance, then the only acceleration is due to gravity, and so the constant 32 feet over second squared will be useful when modeling this situation. If you analyze the horizontal and vertical components of the trajectory with a little calculus thrown in, it turns out that the horizontal displacement you will experience can be modeled using trigonometric function.
All right, so again, knowing that we have to take this from just being a algebraic problem or a trigonometric problem, right? Talking about angles, we have to also adjust that accordingly, be based on other forces, right? So outside forces that are truly existing in the real world there. All right. And then the force that we cannot ignore is obviously the force of gravity. All right, the force of gravity. Okay, so we have to take that into consideration. All right, and that's a pretty big one that we can't ignore. However, something like wind resistance, right? Wind resistance, we will deal with later, right? So that would be something a little bit further on, like in your calculus career, and even if you decide to, go into math later on, you'll learn more about how to incorporate those later on. But in general, okay, something as big as gravity, we have to take in consideration here. All right.
This equation means that once you set the angle and the initial velocity, where you land is completely determined.
Woo! Okay, so hopefully you were able to notice right there. Okay, so once we figure out our angle of our cannon, right, we can turn this into a right triangle here. We can turn this into a right triangle. All right, and then based on this, obviously we can solve for the different components of this triangle and how does that relate to our overall distance that we are going to cover, right? We can do multiple things like that. All right, so if we get into this study here, all right, first off, okay, we've got our trig identities here. Okay, we've got our trig identities here. Okay, and it's saying use them or lose them. Right, so the more you get familiar with utilizing these trig identities, the faster they're going to come to you. All right, the more you use them, the faster they will be able to be recalled here. Okay, now I do not have these off the top of my head. All right, except for a couple of them. All right, I don't have all of these off the top of my head right now, right? But you can use your study sheet. And again, the whole goal is not for you to memorize these. It's for you to get familiar. All right, so again, the first one I obviously gravitated towards is one of those first three Pythagorean identities. Okay, that's the one that I gravitated towards. Okay, then yesterday we talked about different products, right? So I'm gravitating towards the ones that I know, right? I'm going to gravitate towards the ones that I know. All right, and I believe, oh, nope, I was wrong there. There we go. All right, so all I'm doing here is trying to match these up and trying to pick out familiar patterns here. All right, so then once you get down to the ones that you don't know, right? So obviously I didn't know this one off the top of my head here. I forgot it. Ah, Miss Judy, I stink, right? So if you forget something, right, try them out and then take a moment, right? Take a moment and really try to match them up as to how you got there, right? How you got there. So, okay, right, maybe this identity was a little bit more complicated. Why is that? Okay, refresh myself. All right. And then going back through and finishing that up here. All right. So again, just try to make sure that you can match these up. This is trying to get you familiar with it. So please, please try that. Okay. But now that we look at, we understand these functions, right? We understand how we got there. Okay. We need to realize where can these be used at? All right. Where can these be used at? So if we look first at our sum and difference formulas, okay? That's talking about when we were inside, we're trying to figure out what the answer is when we add two angles or subtract two angles, right? And obviously, a good problem there would be looking on our unit circle. But if we're trying to get outside of these math functions only being used for math, we can look at utilizing them further, all right? But first here, we're being asked to prove our summation formula for tangent. Okay, we're being asked to prove our summation formula for tangent. All right, so the left-hand side starts with a sum of angles. All right, so it's easiest if we start here because we know that there is an equation to change our tangent summation into, right? So we know that this summation here can be equal to this based on our formula that we talked about in yesterday's lecture here. Okay, once we get it down to there, we can evaluate for some of the angles, right? And again, pi over 6, we can evaluate for there. All right, and since pi over 6 is 1 over square root of 3, right? Anywhere where we have tangent of pi over 6, we replace with 1 over square root of 3. All right. Then what we can do here is we can factor out a 1 over 3 from the numerator and from the denominator. Okay, we can factor out a 1 over 3 from the numerator and from the denominator. Okay, and then they cancel out, right? They cancel those guys out, and we've gotten our resulting here. All right, and hopefully what you're noticing is that when we factor a 1 over square root of 3 out of both of these, all right, well, since tangent doesn't have a 1 over square root of 3, we have to have it be multiplied by that square root of 3 factor there. Okay, we have to have it being multiplied by that square root of 3 factor. All right, so we don't just factor out because technically there's no square root of 3 here, or there's no square root of 3 here. So we have to make sure that we are using appropriate algebraic skills here. All right. And then if we've got a cosine and we're doing our difference here, we can start to simplify. All right. And again, we need to have offhand those equations. All right. Have offhand those equations. So what that's going to look like, since we're taking the difference between them, right, we're going to have the subtraction here. And they both start with cosine, great. And, all right, they both start with cosine. Okay, and this is the direct equation for our difference here. Okay, so this is our u value, this is our v value. We just plug it directly into our equation here. Okay, we plug it directly into our equation. All right, and then offhand, knowing what the angle of 5 pi over 3 and knowing what the angle of 5 pi over 3 is, right, for the sake of time, I'll just pick the first one. All right, and again, knowing these offhand offhand or having access to them really quickly. And I know that I'm getting like all of these wrong here, but that's because I want to make sure that we get to cover all of this within our time frame, okay? But taking a second and actually looking at what those mean, right? You could even plug it into your calculator here, or just look at a unit circle from earlier units where we had them all written down, okay? But 5 pi over 3 is going to give us 1/2, all right? And then sine 5 pi over 3 would give us this negative square root of 3 over 2, okay? It's going to give us that value there. All right, and then once we've got both of these here, we can factor out a 1/2 from both of them. All right, we can factor out a 1/2 from both of them, and then we're left with this final expression here. All right, and we could try to simplify further, but that's pretty simplified itself. It's in terms of sine and cosine, right? Nothing squared, it's all individual here. So it's pretty standardized with this one. Okay, so again, really it's about putting it all together and like I said, making sure that you've got all your references at your hands here. Okay, so then if we go and try to get a little prequel into what might this look like in calculus here. Okay, what might this look like in calculus here? All right, we might have this equation where we have sine of x plus h minus sine of x over h. All right. And it's looking at an equation like this here, all right? And for now, what we can do is we can interpret this as a rise over run, okay? Or the slope of the red line, okay? We're looking at the slope of the red line, all right? So if we were trying to find an instantaneous rate, that would be a good example of how to do this here. Okay, we're looking at our rise over run here. Okay, because we're looking at the difference between x and x plus h, which is our h value, and then using our trig functions here, we know that this is sine of x plus h minus sine of x. Okay, so then if we look at this here, okay, if we look at this and we try to practice, okay, we can change our numerator here. We can change our numerator into this longer expression here using our rule for our additive identity. Okay, so all we do is, again, is just replace in our values of h and x for the corresponding values here. All right, once we've got them there, okay, we just rearrange some things. All right. We can rearrange so that if we look at this first term here, if we look at this first term and this second term, they both have a sign in it, and I understand that this last one does here too. But if we look at just these first two, we can factor out a sign so that we have cosine h minus 1. Okay, we have cosine h minus 1. All right, then what we can do here is we can take both of these new factors here, and we can put them over our h value, right? So we distribute h to both of those values, right? So writing each of them as a sum of the quotient, right? So dividing both of them by h. All right, and then this gives us our new equation to work with here. All right, it puts it in terms of individual values. All right, so our sum identity shows us this new equation here. Okay, and this might look a little bit more complicated, right? But what this does here is this allows us to look at sine of x in terms of an expression right here, and cosine of x in terms of an expression right here. So if we actually look at what those look like on our graphing calculator, sine of h minus 1 over h and sine of h over h, okay? We can look at both of them, all right? And hopefully you're gonna pick up some things here that neither of these functions is defined for h equals 0. So we can see that the values of h close to 0, right, get really, really close to 0. So if we look back, right, if we look back at our original expression here, all right, h is getting closer and closer to 0. The red line begins to look like the tangent line to the graph, okay? So what this is saying here is that as we move our slope closer and closer to this 0 value here, closer to our x equals 0, okay, it's going to start looking more and more like the graph of the line, all right, the graph of the line. So what this is saying here is it's getting closer and closer to cosine, all right? It's getting closer and closer to cosine. All right, and again, reason being, if I look at 0, right, if I look at 0, as I get closer and closer, it's going to start fighting each other. All right, so then if we look at double angle formulas, okay, we look at double angle formulas. So again, you have your cosine of 4x. It looks like this value using our replacement, right? If we were to simplify cosine of 4x here, we would use our double angle reasoning here, okay? And we would continue to simplify this again using our double angle, okay? We would use it twice here, and then we could simplify down our expression out, right? We could simplify down our expression out, all right? So if we look here, at cosine, of 3x, all right, we look at cosine of 3x here. So it's easier for us to simplify if we write it as an additive property here. All right, and the reason that is because we did not talk about something in terms of an odd number, right? So 3x, but we know that we can write this as the additive property here. And then when we have this as our additive property here, look, we can notice that, oh, we have a double angle right there. We have 2 times our x value, okay? So we're going to, again, separate them out using our additive property and then utilize this double angle here. So if we look here, okay, we're going to use it as our additive property. All right, and we have our cosine and cosine and our sine and our sine. All right, and again, this is where having those equations offhand are going to be really helpful for you. All right, so our cosine, cosine minus sine, sine, and again, plugging in our values for our a and our b there into our equation. All right. Then what this is going to turn into, is we have cosine of 2x, right? Cosine of 2x. So that's going to turn into our double. All right, our double angle here. All right, so it's going to turn into our double angle. All right, using our double angle formula there. All right, then sine is going to turn into our double angle as well, right? Using our sine double angle. All right, once we've gotten them there, okay, we're going to distribute out this cosine to both of these values and this negative sign to both of those values. Or sorry, for this one, it's just to the one value. So it's going to make that sine squared, cosine squared, and this one's going to have a cosine and then a cosine sine squared x. All right. And hopefully you can notice here that just because it's cosine sine squared or sine squared cosine squared, since they're multiplied together, it doesn't matter the order. All right. So we can combine both of these values here for 2 cosine x sine squared x, right? So we can simplify them down to just this 4 cosine x sine x squared. All right, so we have that simplified down there. All right, and then we know that sine squared x is equal to 1 minus cosine squared x. So we can replace that. We can then distribute our 4 cosine x to both of those values. We can simplify. Right, we can simplify down, and so we can see that our formula for a triple angle is now going to be this 4 cosine cubed x minus 3 cosine x. okay? And I know there's a lot of steps to get there, which is why, again, I'm trying not to go too in-depthly into this, because I really, really personally believe you've got to take some time and work through these on your own here, okay? I just want to try to hit the highlights for you. All right. So again, if we look at the double angle formulas for secant and cosecant, all right, here's our identity, and we can go through maybe one or two of these here, but looking at the reason behind that, again, cosecant is just 1 over sine, okay? So a double angle is not going to be any different here, all right? So you still write it as this is our first identity, or one of our first identities that we know, right? The relationship between sine and cosecant, all right? And then from there, all we have to do is replace sine of our double angle with its new relationship here of 2 sine 2 sine theta cosine theta. All right, this is just a quick replacement there. All right, and then based on that, we can simplify down just to make this 1/2 times by 1 over sine gives us cosecant, 1 over cosine gives us secant. Right, so that's how we can get this to this original identity here. All right, same thing's going to happen for secant and cotangent. So start with secant. What does secant actually stand for, right? 1 over cosine. All right, and then this is a double angle, so you replace the double angle, right? All of that lovely stuff. Same thing with cotangent here. Okay. So then, now that we have some new equations under our belt here, we can go back and look at our human cannonball calculation. All right, so of course, like we said, the key here is safety. It's also going to be assuming that there's no air resistance. All right, no air resistance. We're going to try to make this as simple as possible by taking into consideration only the major things that are going to have an impact. All right, so this is something I wouldn't expect you to know offhand, right? This would be an equation that would be given to you, all right? So our horizontal displacement is given by this equation here, all right? And theta is our initial angle, and V0 is how fast we're going, being shot out of the cannonball, all right? So let's take a look. All right, so again, here's our angle. All right, and we're looking for our horizontal displacement here based on this equation. So assuming that the velocity is 60 feet and the angle is 33 degrees, okay, what is the horizontal distance traveled? All right, and what you would do here is you would just plug in for the values that we have. So we said that V0 is our initial velocity. So our velocity here is going to be 60. So we're going to plug that in, and we're going to have 60 squared. All right, we're going to have 60 squared. Our initial angle is 33 degrees. So we're going to have sine of 30, cosine of 30. Sine 30, cosine 30. Beautiful. All right. And then lastly here is this gravitational constant. This gravitational constant. And we worked with it in the earlier lessons here. But if you write it down, it'll be super helpful. The gravitational constant is 32 feet per second squared. All right. 32 feet per second squared. All right, and let me tell you, there are multiple constants for gravity. All right, the key here is what units are you dealing with? We're dealing with feet per second squared. Right? We're dealing with feet per second squared, so that's going to be the key here. All right, and if we do the math right, we plug it in and we get this value of 102.77. All right, and hopefully, based on your experience with unit cancellation here, or dimensional analysis in chemistry, you've got feet squared, second squared, over feet per second squared. So second squared and second squared are going to cancel. Feet squared and feet are going to cancel. So you're just left with 102.77, and the unit on this will be feet. The unit on that will be feet. All right. So then if we were to look, we can assume that our initial velocity is going to be 75 feet per second. All right, so our initial velocity is going to be 75 feet per second. All right, so then the next question is going to be, All right, the next question is going to be, what is the maximum distance we can travel? All right, what is the maximum distance we can travel? So what we did first here is we took our original equation here, plugged in that we are going to constantly be at a velocity of 75 feet per second over our gravitational constant of 32 feet per second squared. All right, so all they did here was they just simplified this down to start off with. Okay, they simplified that down to start off with. And then what we can notice here is that 2 sine theta cosine theta is just our sine of 2 theta here, right? It's just our double angle identity, right? So when we're trying to solve for different values of theta, it's going to be easier if we can just do sine of 2 theta instead of having to plug in sine theta cosine theta. All right, so if we're being asked to look at our maximum horizontal distance, okay, what we can do here is we can assume, right, we know that our range of sine is going to be from -1 to 1, right? If we remember our original graphs here, our sine, right, sine can only go from -1 to 1, right? It can only go from -1 to 1. All right, and we're asking, what is the maximum distance or the largest horizontal distance that we can travel, right? So sine, right, the largest sine can ever be is +1, right? Our base function of sine, the largest it can ever be is +1 here. All right, so therefore, our sine of our angle here, the largest that this can be is a +1. So if we took our value of 175, right, and we multiplied it by sine of 2 theta, which can only be at its largest, a +1, the farthest that we can travel here is this 175.78 feet. Okay, that's the farthest that we can travel here. All right, and then it's saying, what is the initial angle that we need to achieve this maximum horizontal distance? All right, what is the maximum angle that we need to achieve this horizontal distance? And the question is asking for us to solve for theta. All right, our solve for theta. All right, and this is asking us basically, where does sine of 2 theta equal 1? Where does sine of 2 theta equal 1? And if we think back to our unit circle here, that's at pi/4. That's going to be at our pi/4 angle, because that's where our value is going to give us this 1. All right. And again, this is going to be pi/4 and not pi/2, because remember, you've got this 2 value here. You've got this 2 value here. So sine of normal theta, right, pi/2 would give us a value of 1. But since it's 2 times this angle, right, pi/4 is going to mimic what pi/2 looks like to give us our sine value. All right, oh, perfect. We were shot out of the cannon. All right. Then assuming that our net is 150 feet away horizontally, at what angle would you set the cannon to ensure that the net catches you? All right, so this calculation is a little bit more involved here. So obviously we would need to divide first to get our sine by itself. Then we've got our angle, or sorry, our feet is equal to sine of 2 times our angle. All right, so looking at the angles for theta, of course, we'd have to take our inverse of sine function here. We'd have to take our inverse of sine function. All right, and when we do that, we figure out that it can be at 0.51 radians or 29.22 degrees. All right, and that gives us our first answer. But remember, our calculator doesn't give us all possible answers. It only gives us 1, usually in the first quadrant. So we always have to think of, is this the only angle that will work? All right, and technically, right, technically, we have other values that will work here. We have other values that will mathematically work out here. All right. However, let's use some brain power here. Okay. If we have anything that's not in this first quadrant, right? It was talking about if it was in quadrant 2, that would be shooting us backwards. If we're dealing with quadrant 4, that would be shooting us into the ground. All right. So we have to be careful to make sure that we have only answers that keep us in this positive quadrant 1 here. Okay. So then we have this in terms of our squared identities. All right, and again, for the sake of time and for your practice, I'm gonna let you guys do this one here. But basically, you're gonna keep reducing, and you're gonna look at the different properties here, and how do we get to them, right? And how do we really get to them so that we can come here and we can do these practice problems. All right, and again, I don't want to spend too long with it because it gets really wordy and really equation heavy very quickly. All right, it gets very equation heavy quickly. But I don't want you to overwhelm yourself here. All right, that's why I'm not spending too long going over it, because you need to take these at your own pace. All right. The key here, of course, is always having these with you and just working through it step by step by step, trying to figure out what can I simplify here, right? What can I simplify? All right, obviously in this first one here, right, we look at, okay, well, I've got an addition and I've got a subtraction, so you can simplify both of them, right? And those are some things that we should be able to pick up here. And then, of course, obviously after that, it becomes just algebra here. All right. Same thing with our half angle identities. All right. If we look at cosine of 30, all right, what that's looking here is that's cosine of 60 divided by 2. All right, 60 divided by 2. So if we know that, right, we can rewrite our cosine of 30 as this expression here, 1 plus cosine 60 divided by 2. Or simplify further. We can get cosine of 30 is equal to this square root of 3 over 2. All right, and I know we already know that one, but where would that become more handy for us would be right here. Like if we're looking at cosine of 7.5, if it asked you for an exact answer, you'd have to give it in terms of square roots and pies and all of those values. So if we're looking at something like this where we don't know that answer off the top of our head here, okay, we can use our identities that we know, and we can use the angles, our reference angles that we're more comfortable and familiar with. So looking at this, right, cosine of 7.5 is just 15 divided by 2. Right? It's just 15 divided by 2. All right, and since we know that, we can use this equation here, we can rewrite it, and then this would give us our exact answer. And no, it does not look friendly at all. All right, but we can plug this into our calculator if we needed to, right? We could plug that into our calculator if we needed to. But again, these are becoming really, really important when you're getting asked for specific values of angles that are not as nice as our lovely reference angles there. Okay. Then you could even use this half angle identity to approximate the value of pi. All right, and I'll let you read that on your own here, but basically, if you look, you can fit a triangle inside of our unit circle. You can fit multiple triangles inside that triangle here, and you can then try to approximate this value of pi, since our radius for our unit circle is 2 pi. All right. So again, they're looking at this, recalling that sine is opposite over hypotenuse, and then cosine is adjacent over hypotenuse. They can look at the radius, or they can look at it based on area. Okay, based on area. So for them, they've got area equals 1/2 base times height, right? 1/2 base times height, because that's how we could get the area of a triangle here. And then they can look at at this, and they can get a value of 1.29, which again is not a very good approximation of pi, since pi is 3.15. All right, so what they can do there all right, is then put in multiple triangles. So a lot more, okay? And if you look at it without the angles, right? If we're able to fit a lot more triangles than just our basic 30, 60, 90 triangle here, right? If we put it in a different shape, we're able to approximate the value of pi to be a lot closer, all right? And again, all it's doing is splitting up a shape that we don't know the answer to into things that we know how to solve for, right? So it took this circle, split it into a triangle, all right? Well, that didn't work the way we wanted it to, so we split it into more triangles, got us closer. We can split it into more triangles, and it'll get us even closer, all right? And what we can do is, of course, get those values and multiply by the number of triangles we have in order to get our area here. All right. Same thing here. If we were to look at a 24-sided polygon, okay, even more triangles inside of it. Obviously, it's making that graphic, but they're really tiny triangles inside. We get even closer. All right. And if we kept going, we would keep getting even closer. Right, and the conclusion is that each time we double the sides and use the half angle formula to compare the angle, or sorry, compare the area, our approximation obviously becomes closer, right? It becomes closer. And if we were able to double our sides 15 times, we would get a 98,000 sided polygon. All right, that would be insane. 98,000 sided polygon. All right. With 196,000 congruent triangles, all the same size. All right, so we would take every single triangle, multiply by their area, and we would get a really close value for our approximation of pi here. Okay, so of course, your best friend is going to be this study sheet here. All right, so writing the equivalent expressions, knowing them, all right, having them offhand is going to be really helpful, along with, there you go, triple angle identities, our double angle identities, our half angle identities, our product to sum identities, all of those ones that have been introduced throughout this, right? Writing them down, because again, the more times you see them, the more familiar you're going to get with them, right? And even I'll be the first to admit it, I don't know all of those offhand, right? And I'm teaching the course, but I'm a firm believer in you don't need to memorize things, right? At this day and age, we've got Google at our fingertips, right? So it's not about memorizing the equations. It's about being familiar enough with them that it triggers something in your brain that says, oh, hey, I need to go and I think I have something that I can replace this with. Right, and just following through step by step to making this an easier equation for you to use. All right, so then if we go to the checkup here, of course, we're going to look and try to show that these two are equivalent here. Same thing, find all the solutions. Well, we probably want to change this into something a little bit nicer here so that we can solve and have just one value we're looking for here. All right, same thing with the rest of these guys. All right, and I personally really love the ones that are in terms of general, right? So the general product to sum formulas. So making sure you use that and keeping track of them. Okay, and of course, please make sure that you go through and try these. I know, like I said, I know all of Unit 4 has been pretty hefty and meaty, especially on the equations. So take as long as you need to go through this unit, right? You have no homework this weekend, so please take as long as you need to do that, all right? And that really kind of finishes this unit 4.3, all right, our applications of our identities here, all right? And when you get the chance this weekend, once you're done with unit 4 here, you're going to come and wrap this unit up here, and you're going to take at least just this CST. If you want to do the practice and submit it, you can get some extra credit there, and you can get some extra credit for the discussion questions here. All right, so please, take advantage of these opportunities if you want them. And then you have your CST, which should be unlocked here. Okay, so again, just a reminder, there's no homework except for you to get caught up and finished with unit 4 by Monday morning. Okay, that's kind of your goal, Monday morning. All right, tomorrow I will be emailing all parents updates sometime tomorrow, probably tomorrow afternoon. I'll send an update to parents as to where you're at with your progress. All right, letting them know kind of what we're doing. All right, and then obviously next week is our last week of Zoom meetings. So we will cover unit 5, unit 6, and then my goal is the only thing that you should have to work on over the solo week is your final exam here. If you've been keeping up to date, the only thing you'll have is your final exam, okay? But of course, let me know if you have any issues, if you have any questions, comments, or concerns, especially, of course, if you're having issues seeing the graphs here. All right, so based on the 2 people we polled, whether you're on your iPad or on your laptop, it seems like Google Chrome app or browser is kind of key here. All right, also, of course, make sure your iPads are up to date. All right, if you're having issues with your iPads, switch to your laptops or computers if you have access to one. If it's still not working or you don't have access to a laptop or computer, please email me and you and I together will make arrangements for you to take your quiz elsewhere. All right. So please let me know and we'll make arrangements for that. Okay. Other than that, guys, have a great day. Spend, the rest of this time here working and getting caught up on this stuff for Algebra 2. And I will email you tomorrow and we'll be in contact if you need me. All right. Have a good weekend, guys. I'll see you Monday.